He obtained his doctoral degree and master's degree from the Department of Engineering Design and from the Department of Applied Mechanics of IIT Madras, respectively. He obtained his bachelor's degree from DEI Deemed University, Agra. Dr. Amol's research expertise are on understanding the microstructure evolution in metallic systems using continuum phase field simulations and discrete models, which is molecular dynamics. Currently, he is also exploring the fracture mechanics of adhesive bonded joints and 3D printed polymer components. I wholeheartedly welcome Dr. Amol to please give us proceed with this talk for the day. Dr. Amol, you can please take
Thank
over.
you. Thank you. I hope I'm audible to everybody. I'm audible?
Yes, sir, you're audible.
Yes, sir.
Yeah, thank you for the introduction and good evening to all the participants. Before beginning the talk, I would like to tell all of you that I joined this institute called Birla Institute of Technology and Science, Hyderabad campus in the year 2019. And after finishing 1 year in this institute, I was given a chance to offer a course called Fracture Mechanics. I was so excited by this course that I started exploring the research possibilities in this area. And there are numerous topics which are yet to be addressed. And so I somehow got into this area, and I've been exploring this area past 2 years. And in the last 2-3 months, I have been exploring about the computational aspects of the fracture. And this presentation is going to give you an overview about the theory and the computational aspects of the fracture mechanics. Since even people who are from the mechanics community are at times not exposed to this area, I just thought of giving you a brief overview about why this topic even started and what is the pioneering work in this area, which will be followed by a brief introduction about one of the famous computational fracture mechanics techniques. Okay. So we'll start with what is material failure. So everybody knows that failure is a condition where component or part ceases to do its intended operation. And failure could be of so many types. It could be a yielding of material, it could be a buckling, it could be a fatigue failure, it could be creep, it could be wear, it could be degradation because of some chemical attack, or it could be a fracture also. So fracture is definitely one of the failures criteria. So fracture is nothing but it's a separation of an object or a material into 2 or more pieces under action of an applied stress or a stimuli. Okay. So whenever there is a fracture, there are certain discontinuities which are generated in a component, and definitely displacement discontinuity is one of the discontinuities. Okay. So designing structure to avoid fracture is not a new idea. So even if you go back to ancient Egyptian or Roman structures, they are still standing today. It's a testimony that the designs were very efficient even in those days. And some of the examples are the pyramid and Roman constructions. They are still there. For example, the Giza pyramid is still there, standing safe. The reason is that these structures were made in such a way that the crack propagation or a fracture was avoided to the greatest possible extent by designing a system or a structure in such a way that majority of the structure was under the state of compression. If it is under the state of compression, then failure of a structure due to the fracture is something which is highly impossible. Okay. In fact, there are still many bridges and buildings in Europe which are still there. That is an indication of the fail-safe design. So even if you look at some of the Roman bridges, so those bridges were designed in such a way that whenever there is a vehicle or a chariot passing over, the structure, the arc-shaped structure was under a complete state of compression, and that has prevented any crack or a fracture to happen. Okay. However, all these structures are primarily made of brick and mortar. They are heavy, they have a lot of material into it, and they are primarily made of brick and mortar. But with the advent of the Industrial Revolution, there was a mass production of the iron and steel. This led to incorporation of metals into the designs and structures. Okay. One of the famous structure you can see in this picture is the London Bridge, Tower Bridge, London. So you can see that there are so many cables, etc., over there, and they are there to take the tensile load. So by incorporating the metallic components into the structure has definitely played an important role by reducing the weight of the structure. At the same time, it is not compromising its strength. However, these structures are having the elements which are going for the tensile loads, and that has resulted in fracture or a damage of the structure with the passage of time. Okay. So when steel was replacing the structures, there were certain accidents which has occurred, and those accidents have led to the development of a field called the fracture mechanics. There were several such instances which happened in the history and that motivated researchers to get into the details about what could be the potential reason for a fracture of a component of a system. One of the very famous incidents that took place in the Boston was the bursting of molasses tank. So this is one of the very famous incident which has led to the researcher to go into the details of investigating what is the fracture and what is the crack propagation. Okay, so this accident was so severe that the stench of the molasses existed for several months, and this accident causes 12 deaths, 40 injuries. So there was a tank which was carrying the molasses, and suddenly this tank got burst, and it led to death of several people, and the stench of molasses existed for several months. So what could be the potential reason for this tank to actually undergo burst? So some factors that led to the disaster are the steel balls were too thin to support the weight of the full tank of molasses. Flawed rivet design was also a problem. Stresses were too high on the rivet holes, and the crack initiation started from there. So the riveted hole itself were the site of a crack to propagate. Overfilling of the tank that built too much of pressure, and negligence in the flaw inspection. So unfortunately, the color of the outer color of the tank was same as the color of the molasses. So even if there was any flaw or defect, it was not visible, and that has led to such a fatal accident. There are other instances also that took place. For example, there are ships called cargo ships or liberty ships. Those ships were primarily made of welded structures. So initially, before the welding was even invented, the ship were made of riveted structures. Slowly, the riveted structures were replaced with the welded structures. But the welding has brought many issues. These welded ships, when they were traveling in the Atlantic Ocean from USA to Germany, they were traveling in the cold water, and the base of the ship was having a hot oil. So there is a hot fluid and there is a cold fluid. Because of the thermal mismatch, there were crack formation, and that has led to the breaking of ships into two pieces. And there were several hundreds of ships which have broken in such a way that again caused the scientists and researchers to start thinking about what could be the potential reason for this fracture to happen. Similarly, there was explosion of jet planes during the World War in 50s. Okay, so these jet planes actually used to get burst in the air, and these are the incidents which have primarily motivated researchers and engineers in the mechanics community to start exploring about what is crack, how it is generated, how it is propagated, and that led to the field called fracture mechanics. Okay, so with the development of large ships made of welded plates and high capacity jet planes, the predominant question asked was, what causes the failure? Can we prevent the failure? This question resulted in a new discipline of engineering called the fracture mechanics. So fracture mechanics primarily involve study of behavior of solids that crack under various conditions. And fracture mechanics has got two viewpoints. One is the mechanistic viewpoint. So where we only care for the mechanics aspect of the fracture, it's primarily involved. What are the stresses, displacements, in the body with the crack and how those stresses and displacements are going to cause the crack to start propagating in a particular direction. So we don't care about how the microstructure of the material look like. We only care about how the domain of interest has the structure, has the displacement and stress distribution, and how it is going to lead for a crack to propagate in a particular direction. So this is the mechanistic viewpoint. There is another viewpoint which is called as a material science viewpoint. So when it comes to material science, we care for what is the microstructure is going to play a role in deciding the crack propagation and fracture. And we know that the material microstructure, especially metals, primarily consists of grains and grain boundaries and triple junctions. So grains are the regions in which your atoms are arranged in a systematic manner at a particular orientation. And a typical polycrystalline material contains several such grains which are oriented randomly. And these grains are separated by an amorphous region called grain boundaries. So grain boundaries are the potential sites from which the failure or fracture is initiated. So how these grains and grain boundaries going to play a role in the fracture is going to be investigated by the material scientists. So this is another viewpoint of the fracture. So if you look at any fracture process, it is observed that sometimes the fracture happens along the grain boundary, which is called as an intergranular fracture, as shown in the bottom left figure. It is also possible that grain cuts through the grain. So crack cuts through the grain. It also encounters boundaries at times, but mainly the fracture is happening within the grain, which is called as a transgranular fracture. Okay. It is also possible for a metal to show ductile fracture, where it has been observed that when you start pulling the material at a large deformation, the voids, etc., start creating inside the materials, and further elongation of the material causes these voids to travel and meet at a point, and once they start meeting together, there is a big void created. This void is further propagated to cause the fracture process. One of the famous fracture process which you observe in tensile testing of a steel is called as a cup and cone fracture, which I have depicted over here. You can clearly see that these voids are joining together, and those voids are initially of micro-sized voids, but once they start joining, they are going to create a macro-sized void, which finally grows and breaks the material or component into the two pieces. Okay. So these are the viewpoints of the fracture mechanics. In this presentation, I'm primarily focusing on mechanistic viewpoints of the fracture mechanics. Okay. So fracture mechanics is based on an implicit assumption that there exists a crack in a material. Every material has a crack. This could be a macro crack or could be a micro crack, but crack is always there. The crack can be man-made, natural, or created due to the externally applied. Okay. So it could exist in the form of a slag or some heat-affected zones. Okay. So these are also some kind of discontinuities or crack. And also, dangerous crack can be nucleated and grow during the service of the bond. So the fracture mechanics deal with one question: is known crack is likely to grow under a given condition or not? Okay. So the question is that when fracture mechanics was not there, was that not possible to build the structures? Well, you could have built the structure, but the only thing is that in order to prevent the cracking of a material or a component, the structures were built very heavy. So there was a lot of compromise on the volume of the material. So you end up making structures which are very bulky. And those kind of things are unwanted in certain scenarios. For example, if you are making an aircraft, you have to really make a beautiful compromise between the strength and the weight. Okay? So that aid was provided by the fracture mechanics, which has led people to come up with a design where you can improve the strength of the material at the same time do not compromise on the weight side. Okay? So a large part of ambiguity has been cleared with the development of the fracture mechanics. Okay. So fracture mechanics also enable designer to use much lower factor of safety and thus reducing this weight of the component without compromising its strength or performance. Okay. So fracture mechanics primarily deal with the cracks. The cracks could be 2D cracks, planar cracks, or the embedded cracks. 2D cracks are very simple. They could be straight crack or curved crack in any 2D structure. Planar structure could have cracks. These cracks could be a through crack or they could be a partial crack. You can also have a 3D crack, which are completely either embedded within the body or they could lie even in the surface. Okay. So different kind of cracks are actually taken care of in the fracture mechanics. And these cracks could be primarily subjected to three kind of load. One is called the mode 1, where the crack is subjected to a load that is perpendicular to the crack front or a crack surface. Similarly, you have a mode 2, where your crack front is subjected to the shear. And third one is the mode 3, which is also called as a clearing mode, okay, where the load is applied parallel to the crack front as well as crack surface. Okay, so crack front is nothing but it is the tip of the crack in 2D settings, and when it is extended in 3D, it becomes the crack front. Okay, so these are the three possible modes of these are the three classical modes of the fracture, but in reality, you can have a scenario where your component is subjected to combination of any of these three fundamental modes. Okay, so this is some kind of a prerequisite before I go further. Okay, so once we have a crack in the body, a mechanician will say that, okay, let's look at what is the stress and displacement and what is the criteria for a crack to occur. So the most fundamental way people started with looking at the material from the atomistic point of view. So they said that the material is made of several atoms. Those atoms are placed in systematic manner. So when you are applying the load on the system, basically these atomic bonds are getting stretched. Okay. So if you keep applying the load, this bond will be keep stretching and stretching. A critical point will be achieved, after which the strength of the bond will start lowering down and it will not be able to take as much as load it used to take. And finally, it will break into the two bonds. Okay. So a classical behavior of any atomic bond is shown on the figure on the right side, where you can see that you are applying a tension. There is a critical point which is attained, and once this critical point is attained, the bond is not taking load any further. In fact, with further stretching, the load is coming down. So this kind of a behavior was considered to compute the critical stress for a material to start fracturing. I will not go into the mathematics, but from the mathematics, it is observed that the critical stress from these atomistic models shows that the sigma c is equal to modulus of elasticity E over pi. Okay. So if you take, for example, mild steel, which is having elastic modulus of 210 GPa, the fracture strength from this formula comes out to be 70 gigapascal, which is highly impractical because when you see in real life, the strength at which mild steel specimen breaks is from 400 to 700 megapascal. So clearly the atomistic modeling approach to predict the critical stress at which your crack will start propagate is highly unrealistic. Then people start looking at the continuum models by following the theory of elasticity approach. And one of the famous analysis done by a scientist called Inglis is shown here, where he considered a plate and he introduced an elliptical crack. And then he observed that if any plate having such a crack, of course the plate is infinite in size. So the maximum stress in this plate is equal to sigma naught multiplied by 1 plus 2a over b, where 2a is the major axis and 2b is the minor axis of the ellipse. So sigma 22, which is, so 22 is something which is the direction to y direction, you can say, which is equal to sigma naught 1 plus 2a by b. Okay. So let's see. So here it is an elliptical crack. Suppose if I start shrinking the minor axis, if I slowly start shrinking the minor axis, let's see how does the elliptical crack look like. So you have an initial crack like this. Let's start decreasing the dimension p. You start decreasing it, slowly this elliptical crack has become a sharp crack. Okay. So for b is equal to 0 limit, it has converted into a sharp crack. So this configuration looks like a body which is having a sharp crack. So let's go back to this formula which was proposed for the elliptical conclusion. If you put b is equal to 0, your sigma 22 becomes infinity. which means that if any body which is subjected to sigma naught is having a sharp crack, the maximum stress is infinity, which is again realistic because it is not possible for a material to take infinite stress. And irrespective of what sigma naught you have applied, it will always show the infinite stress, which is even more unrealistic. So even this theory also got failed. So now the question is that how should we go ahead? So with this, there is a scientist called Griffith who proposed the criteria for the brittle fracture. He said that let's take a body which is having a crack of area A, which is subjected to some loading sigma. Okay, if this body is subjected to load, then by invoking the law of conservation of energy, you can say that the work performed on the body per unit time is going to be utilized in increasing the internal energy of the body, the kinematic energy of the body, and this work is also going to create an additional surface in the form of a crack. Okay. So there will be energy associated with the formation of a new surface. After all, crack is a surface, and when the crack is propagated, there is further generation of a new surface. So the rate of change of work is going to contribute to what? Increasing the or changing the internal energy, changing the kinematic energy, and also changing the surface energy of the body. Okay. So internal energy has got two components. One is the elastic components, other one is the plastic component. And the derivative we have taken in this expression, W dot E dot is time derivative. We can replace the time derivative, dou over dou T is equal to A dot dou over dou A using the chain rule. So we'll replace this time derivative in the above equation. And by considering the quasi-static condition, once we consider the quasi-static condition, we can even switch off the kinematic energy term. We can just leave it. So by doing it and incorporating both elastic and plastic contribution of the internal energy, you arrive at dW over dA is equal to dou UE over dou A, dou E over dou A plus
इसी पे नहीं कर कूलिंग पे नहीं करता है.
So gamma is the total energy associated with the crack surface.
हाँ, ज्यादा बाहर हीट रहता है तो नहीं करता है, कुछ भी नहीं करता है.
We also know that the potential energy is given as strain energy minus work done.
और तो ये कंप्लेन
So
कर
for
दे
an
क्या?
ideally brittle material, the energy dissipated in
बन
plastic
जाएगा.
formation is also negligible. So we can even ignore the UP effect. Okay, and if gamma represents the surface energy required to form a unit of a new material surface, then you can actually say that dou pi by dou A negative is equal to dou W by dou A minus dou UE by dou A, which is dou gamma by dou A, which is equal to gamma. So this parameter is the total surface energy, which is nothing but the multiplication of the crack surface multiplied by surface energy of the body. So whenever there is a crack propagation, the body has to overcome this energy of the body. Okay? So once the surface energy is overcome, there is a crack propagation. So this theory was completely convincing in case of a brittle material, and it was proposed by a scientist called Griffith. Okay, so there is a scientist called Irwin who dedicated this theory to Griffith. Therefore, the term potential energy release rate was represented by G. Okay. So for a crack to propagate, the body has to overcome the surface energy. Again, I want to re-emphasize here is that this theory is primarily limited to the brittle material. Okay, so when we look at this theory, it doesn't really talk about what is the orientation of the crack, how many cracks are there, how they are merging, how they are meeting. It only talks from the potential energy point of view. It only looks at the potential energy of the body. It says that if there is a crack propagation, the potential energy of the body will go down, and the rate of change of potential energy is equal to the surface energy. So G is equal to 2 gamma. 2 is there because whenever there is a crack initiated, it is going to create two new surfaces. So energy associated with both the surface need to be taken care of. And fracture theories are in general very complicated, although this theory looks fairly simple. But as soon as you incorporate hardening and plasticity, all these effects, the fracture theories become very, very complicated. And doing fracture experiments is far more complicated than these theories. Hence, the best way to understand the fracture processes is to do the simulations. Okay, so now I will go to the simulation aspects of the fracture mechanics. So as I said, that experiments related to the fracture mechanics are difficult, time-taking, very costly. They are sometimes even impractical. So hence the only alternative left is to perform the fracture simulations. Fracture simulations can be carried out by using discrete approaches or a continuum approaches. So in discrete approaches, we model the computational domain itself as a set of particles, and those particles are interacting with each other through some force or a potential. So based on how you are modeling these particles, there are different models which are proposed, such as lattice models, multidynamic simulations, and discrete image simulations. These models are also deal with different time scales as well. In continuum approach, there are two main approaches are there. One is the sharp interface approach. Other one is the smeared interface approach. So sharp interface approach are such as extended finite element or cohesive zone modeling. Other one is the smeared interface approach. My talk will focus primarily on the phase field model. Of course, I will give you some exposure to sharp interface approach. However, both these sharp and smeared interface approaches can be implemented in the finite element settings. Okay. So what is the sharp interface approach? In this approach, the displacement field is considered to be discontinuous across the crack surface. Okay. Two famous approaches of the sharp interface approach are extended finite element approach and the cohesive zone approach. So in this extended finite element approach, generally, we enrich the nodes. So the black color nodes are the nodes which are enriched. They are specially enriched in such a way that they take care of the presence of the crack. Okay. Similarly, if you look at the right-hand side, it is called as a cohesive zone model. In this model, we introduce a special zone called cohesive zone. And these zone, there are special elements which are introduced. These elements have a particular traction separation law. And based on how the traction separation law is given, the fracture behavior is taken care of. Okay. But these two approaches are called the sharp interface approach because they take care of the displacement discontinuities. Okay. So when these two approaches are there, why we need the smeared approach? Because there are certain disadvantages with these two approaches, which are you need to have a pre-cracking. You need to have a pre-cracking in the domain. Second thing is that whether it is extended finite element or cohesive zone model, the crack propagation direction has to be defined a priori. So once you have a notch body, you are going to create a cohesive zone, and the crack is going to propagate only in that zone, which is not practical, especially if you have multiple cracks, they are going to interact, or even if the loading is not mode 1 or mode 2, it is a combination of any of these loading, then it is not possible for you to decide before the beginning of the simulation itself that where the crack is going to go. So another limitation is that you have to define the crack propagation. It is not suitable to model intersecting cracks and micro cracking or even crack branching. These are the phenomena which are not possible to incorporate so easily. Third thing is that you have to explicitly track crack. With every time step, you have to track the interface. So these challenges are eliminated to some extent by the smeared interface approach, such as phase field model, where you do not have any discontinuity in the displacement field, but the presence of crack is taken care by gradually reducing the stress and modeling the degradation process. Okay. So all the limitations of the sharp interface approaches are taken care by the phase field method. Okay. So phase field method does not require pre-cracking, especially phase field fracture method, it does not require the pre-cracking. It does not even require explicit tracking of the crack, and it is automatically taken care of. Crack propagation direction need not be provided a prior. You don't need to provide any direction, you don't need to provide a crack. Just keep applying the load on the component of material. Whenever it finds that there is a need to introduce a crack because it has already reached a critical state, phase field model automatically introduces the crack. It is highly suitable for modeling intersection crack, crack branching, and crack merging. And that's the reason that these days this technique is really catching up, and most of the people who are working in fractional mechanics are shifting from extended finite elements to phase field model, or they are combining the good aspect of phase field and extended and then doing this. So what is phase field model? Phase field model is a method which is primarily used for solving moving interface problems. Some of the examples of the moving interface problems are the solidification, grain growth, phase transformation. So if you look at the grain growth, any microstructure of material contains several grains. So when you heat or subject it to a load, this microstructure, there is a growth. So there are some grains which start growing and some grains which start shrinking. So there is an interface which always moves. So wherever there is a moving interface problem, there is a possibility to introduce a phase field model to study the evolution of a component. Okay. So in the phase field model, a system, microstructure, or region is represented by a single or a set of order parameters. Okay. For example, if you look at the grain I have shown on the bottom right, you need several order parameters to represent grains. On the other hand, in fracture, maybe a single order parameter or single damage parameter is enough to represent the entire grain. So depending upon the problem you are solving, the phase field model has requirements whether it should have single order parameter or multiple order parameters. Order parameter is just a parameter which is representing the domain of your interest. Okay. So once you represent the domain by the set of order parameters, you are going to write the free energy of the system. And once the free energy of the system is written, you are going to evolve the system by reducing the free energy of the system. And thereby you see how the fracture or a solidification or a grain process is taking place in the system. Okay. So now I'm going to talk about phase field model of a brittle fracture. Okay. So the entire presentation from now will cover about some of the aspects of phase field model of the brittle fracture. So this phase field model of brittle fracture is closely related to the variational approach of brittle fracture. Displacement field and the set of crack obtained simultaneously. It uses the principle of minimum potential energy, okay, which is nothing but the Griffith theory. So this variational theory of, so this phase field model of fracture is inspired from the Griffith theory of fracture. Okay, you need not put any additional failure criteria here, unlike the case of cohesive zone or extended finite element. You don't need to put any additional failure criteria. It solves fracture mechanics problem using partial differential equations. And basically it solves two coupled partial differential equations. One is the vectorial displacement field and another one is the scalar phase field. Okay. So what is the difference between a sharp crack model and a smeared crack model, or a sharp crack topology or a smeared or phase field crack topology? Let's look at the sharp crack topology. Here you have a domain. This domain is having a crack. This crack is having a surface area gamma. Okay. It says that wherever there is a crack, the parameter phi, which is a damage parameter or an order parameter, takes the value of 1. So here it will take the value of 1. And wherever it is intact, it takes the value of 0. Okay. So clearly there is a sharp interface between the damaged zone and the intact zone. On the other hand, if you look at the phase field model, it introduces smeared interface where you have phi is equal to 1 representing a complete damage, and you have the phi is equal to 0 which is representing the intact form of material. However, the transition of the complete damage to a complete intact material is fairly smooth. Okay, so there is a smooth function which takes care of the transition between the intact zone and the damaged zone. So if phi is equal to 1 is the complete damage and phi is equal to 0 is the intact material, then what are these intermediate values? Well, These intermediate values of phi between 0 and 1 are nothing but the extent of damage. So what phase field model says that damage is not really sharp. In fact, it is diffused over a certain length. Okay. How much this length has to be? This is a big question in phase field model. We answer it by saying that it should be as less as possible. Okay. So there is a diffusion of a damage over a certain region surrounding the crack. Okay. By giving such kind of a damage, it is very easy to model the crack propagation without explicitly tracking the crack interface. Okay. So phase field model inherently has got a length scale parameter. So if you look at this figure, I'm just highlighting, there is a length scale parameter which is already introduced here, which is 2L0. Okay. So phase field model has got a damage in the smeared form, which also incorporates the length scale impact. So if you look at the discrete model of a crack, there is a body with a sharp crack. The total energy functional of this body is strain energy, which is CV, plus CS, which is the surface energy, minus P, which is the external load. Okay. So the strain energy of the body, if per unit volume is CP, which is nothing but half sigma inner product epsilon, then the total strain energy is the volumetric integral of CE. Okay. Similarly, the surface energy of the body is nothing but total surface area multiplied by the GC, which is critical energy release rate. This GC is nothing but it is equal to 2 times gamma. Okay. So once the body overcomes the critical value of the GC or a surface energy, the crack will propagate. So the energy associated with the crack area is GC multiplied by the surface area of the crack minus P, the load applied. Okay. So while we are solving the problem by considering a sharp crack, we are also making sure that there is a thermodynamic laws also taken care of. You cannot violate the basic thermodynamic principles such that the surface area of the crack always grows. Okay. GC, either it could be less than or equal to the G has to be less than or equal to GC. So the energy release rate G has to be less than or equal to the GC. Or by combining these two, you can say that G minus GC multiplied by time derivative of tau has to be equal to 0. By taking these conditions, you can actually study the crack propagation, but the above formulation treats the crack as a discontinuity and hence presents numerical difficulties in tracking the crack path. On the other hand, if you take a continuous function which is representing a damage, it is easy for you to study the crack propagation because you don't have any jump condition to track the interface. Okay. So once you introduce this smeared form of a damage, all the energy equations are also going to change and the smeared effects need to be taken care of. So the energy of the system will again have the component coming from the strain energy, the surface energy, and the external work done. But since you have the damage diffused over a certain region, presence of damage should also be taken care of in the strain energy. So this new function G phi is introduced while writing strain energy, and this G phi is nothing but a degradation function. Okay. So where there is a complete degradation or where there is a P is equal to 1, your G phi takes the value of 0. Because there is a complete crack, there is no material there. So G phi will become 0. On the other hand, where your phi is equal to 0, where material is completely intact, your GP will take the value of 1. Because there is no. On the other hand, any damage between 0 and 1 has to take care of has to be introduced in the strain energy computation. Okay. Similarly, if you look at the energy associated with the crack surface or the damage area, this energy is given as gamma, which is nothing but crack surface density function. Okay. Since this damage is diffused in this diffuse zone, it is not only the P, even the grad of P also exists. So when you are writing the crack surface density function, it should be function of P as well as the gradient of P. So the surface energy term now will be volumetric integral of Gc multiplied by gamma, which is function of P and grad P, and this integral is done over the volume of the body, minus the external load that is applied. Okay. So the question is that how should the degradation function should be taken? What should be the form of the degradation function? Although it should be 1 where body is intact, and it should be 0 where the body is fully cracked. Okay. So the degradation function typically looks like this. So there are many forms which are proposed by the researchers. So all these possible forms I just showed in the plot. Okay. You must be wondering what is this parameter beta. Beta is something which is extremely small parameter, and in order to, while doing the simulations, there are some ill conditioning that sometimes come up. In order to prevent it, this beta is also introduced over there. But any typical degradation function looks like this. It just goes gradually down from 1 to 0. Okay. So once you have the potential energy written in terms of strain energy, dissipation, and spillover, the next thing is that what should be the form of the crack surface density function. The typical form for the crack surface density function is taken in this way. Okay. I will not go into the details of the derivation of from where it has come. If you want, I can talk to you later over email or something. So as of now, we will take that this is the function which represents the crack surface density, and you can see that it has got two components. One is the local component, first component P square over 2L, and another one is a non-local component, which also depends upon how the surrounding values of V are. So gamma is P square over 2L plus L by 2 multiplied by grad V whole square. Okay. So if you look at the smeared zone on your right hand side, you can observe that grad of P is existing only in this smeared zone. If you go away from this cracked zone, the grad Phi becomes 0. Okay. And there is a length scale parameter also there in gamma expression. Okay. So if you actually say that your L is tending to 0, which means that your diffused or smeared zone is slowly shifting toward the sharp interface. The second term actually goes off, and the first term actually start blowing up. So in a way, this model start moving toward the sharp interface model or a Griffith theory. Okay. So this kind of thing is basically called as a gamma convergence. So this model is fairly consistent in showing that if you go for a small length scale, then this smeared interface approach slowly start moving toward the sharp interface. Of course, this parameter will not be able to work, but these studies are basically called as a gamma convergence. Okay. So once you write the potential energy of the body is written in terms of two unknown functions. One is P, damage parameter or order parameter, and another the displacement field U. So the governing equations from the potential energy are obtained by taking the variationals. So if you take the variational with respect to U, you are going to get the di sigma is equal to 0, which is nothing but the stress equilibrium equation. And if you take the variational with respect to phi, you are going to get another governing equation, which is going to take care of the evolution of the damage. So these two are the fundamental equations of phase field model of fracture. Okay. Now the question is that how the sigma should look like. Of course, sigma should take care of the damage, and sigma is not only a partial derivative of strain energy with respect to epsilon, but also takes care of the account of damage through the degradation function G. And when you are doing the variational of the potential energy, you also end up getting some boundary conditions which are given on the right hand side, where U is equal to U bar and sigma dot n is equal to T fraction and grad phi dot n is equal to 0. So you get set of governing equations and you also get boundary conditions. So once you have these governing equations, you can solve this in the finite element settings and see how the crack propagation is taken care. Okay. So one interesting thing I want to show that here, I have taken sigma is equal to g p del partial derivative of strain energy with respect to epsilon. This kind of formulations bring sometimes some issues. For example, so based on the definition of sigma in terms of how degradation is carried out, sorry, there is a yeah. So based on the definition of sigma in terms of how the degradation is carried out, different formulations such as isotropic and isotropic models are derived in the literature. So there is something called isotropic phase field formulation. So whatever equations I have shown previously are the isotropic phase field formulation. Okay. So if you look at the expression for sigma, it just say that no matter whether strain energy is coming from the compression or a tension, the degradation has to be multiplied, which is not practical. Suppose if a body is undergoing a compression, you cannot have a crack propagation taking place. Okay. So the isotropic phase field formulations have an issue that even if you are having a body with a crack subject to the compression, it still shows a crack propagation, which is not practical. So what is the solution? The solution is that let's take the strain energy and break into the two parts. Tensile component, strain energy coming from the tensile part of the load, and strain energy coming from the compression part. So wherever there is a tension, this tension is going to cause the opening of the crack. So the degradation will only be associated with the tension, strain energy coming from the tension load. Okay. So slight tweaking has been done while writing the potential energy of the system. Once you do that, these are the set of governing equations you will get. Okay. So the sigma is not anymore multiplying the entire strain energy with g phi. Sorry, g phi is not multiplied entirely with the total strain energy. It is only the strain energy which is coming from the tensile part of the load is only taken care through the degradation. The compression is untouched. Okay. There is also something called as a hybrid phase field formulations, which I am not going to discuss here. I am going to talk only about isotropic and anisotropic here. And anisotropic is actually efficient because it prevents the crack propagation under a pure compression state. Okay. With this, we also check for the crack irreversibility. So we know that the damage or a cracking phenomena is dissipative in nature. Any damage model should ensure the damage irreversibility, which means that the crack surface area either remains the same or it will change its area, increase its area. Okay? Which means that gamma dot has to be greater than or equal to 0. And gamma dot is nothing but the volumetric integral of, capital gamma dot is nothing but the volume integral of small gamma dot times dV, which is phi dot del gamma by d phi. So if this has to be equal to, this has to be greater than or equal to 0, then phi dot has to be greater than or equal to 0, and del gamma by del phi has to be greater than or equal to 0 in order to ensure the thermodynamic consistency. Okay, so I will not go into the details. I would rather say that the thermodynamic consistency is taken care by ensuring certain conditions. And most importantly, in phase field model, the crack irreversibility is also ensured. And we also make sure that we always compute the maximum strain energy at every point. And that maximum strain energy is going to be used for checking the crack propagation criteria. Okay. So this is the basic formulation of phase field model, and it has got several applications. So these are the classical set of equations of phase field model of fracture, and they could be used for addressing multiple fracture problems. So here I will show you. So if you take an isotropic phase field model, as I said that it doesn't care whether it is compression or tension. So if you take a body under a state of a shear, this body shows that the crack propagation happen in two directions, which is not true. Okay? If you apply a shear loading, the crack propagation should happen only in one direction. And that is taken care by an isotropic phase field model. And you can see in the bottom figure that if you take an isotropic phase field model, under a state of shear, there is only one direction in which crack is propagated. Okay? Second issue with the phase field model is that the length scale parameter. If you remember, I discussed about the length scale parameter while talking about this diffused zone. So sometimes choosing a large value of length scale parameter also changes the load deformation behavior of the crack body. Although recently these issues have been addressed, and there are some models, I think, which are length scale independent. I have not gone into those details, but the equation which I have shown you as of now have those issues, and one of the issues is the length scale. So we tend to choose as smaller length scale as possible. If you too much diffuse the smeared zone, it is going to cause unnecessary damage to accumulate, and that is going to deviate the material behavior from the realistic conditions. Some of the applications of the phase field model could be seen in the recent times in composite laminates, where you can see that the crack is propagating within the laminate, and also delaminations, etc., are also taken care of. And depending upon whether you have a perfect interface, or you have a stiff interface, or you have a sharp, soft interface, fracture is taken care in a different way. Another application of the phase field model is the pitting corrosion, where there is a degradation due to corrosion and how the crack propagates, because corrosion is also shown through the phase field simulations. Another application of the phase field simulation could be seen in thermoelastic fracture design, where because of the temperature difference in the stresses, how multiple cracks generate, how they merge, how they meet, those things can also be shown by the phase field simulations. Of course, there are some drawbacks. For example, when you have a phase field simulation, as the cracks start approaching the end of the domain, there is a widening of the damage. So this still need to be addressed, and this widening need to be reduced. Second thing, as I have pointed out, they are highly sensitive to the mesh and as well as length scales. Okay? So people are still working to make sure that the length scale sensitivity and mesh sensitivity is also taken care of. Phase field model. Of course, phase field models are yet to be explored in the impact and glass loading conditions. There are not much papers published in this area. So this is also one direction phase field model need to be explored. So with this, I will finish my presentation. And I apologize because my knowledge in this field is very limited. I have been exploring this past 2-3 months only, but I would like to answer questions from your end. Thank you so much.
Thank you, Dr. Amol. Actually, you have covered a very wide area, and it is very surprising